calculate the mass defect and binding energy of sodium-24. And we're given the mass of the hydrogen atom, the mass of a neutron, and the mass of the sodium-24 atom. When finding mass defect and binding energy, we're giving these quantities here, the mass of the hydrogen atom, the neutron, and the atom in question. We use hydrogen instead of the proton mass because it accounts for the electrons in the atomic mass. First thing, determine the number of protons and neutrons in the atom. Well, sodium's atomic number tells us that there are 11 protons. You need to subtract the atomic number from the atomic mass, 24 minus 11, and find out that it has 13 neutrons. So you need to multiply the number of protons by 11. Why? Because there's 11 protons. And again, we're using the hydrogen mass because that will take into account the electrons that hydrogen has, which will then work off the electrons that sodium has, because when you do the mass of sodium, that takes into account its electrons. So you're multiplying the mass of hydrogen by the number of protons, just to say it again, and you get 11.086075 U atomic mass units. Neutrons, multiply that by 13, because that's how many neutrons you have, and then add them together. This is the mass of all the protons and neutrons that make up sodium-24. We see that the mass of the protons and neutrons is greater than the mass of sodium-24. Here's the mass of sodium-24. What is that, 23.99? Here's the mass of its constituent neutrons and protons. The difference between these masses is the mass defect. We subtract the mass of the sodium atom from the mass of the protons and neutrons that make it up. This is the mass defect in atomic mass units, or U. They used to be abbreviated AMU a long time ago, but I guess U is shorter. The symbol for mass defect is delta M. Normally we round in physics class. When doing mass defect binding energy problems, do not round until the very end, or you won't see any difference in the masses. In general, AMUs don't work well with other units, atomic mass units. To solve for binding energy, we need to convert the AMUs to either kilograms or MeV per c squared. So here are the two conversion factors. One atomic mass unit is 1.6605 times 10 to the minus 27th kilogram, or 931.5 MeV per c squared. Now MeV is a unit of energy, and we're dividing it by c squared. That looks kind of unusual, right? The next slide will show you why that makes a lot of sense. So here's our atomic mass units. We convert it to kilograms by, I'm not going to repeat the number again, that's how many kilograms are an atomic mass unit, and we get this many kilograms. Or we multiply it by this factor, and we get 193.53 MeV per c squared. To find the binding energy, use the energy mass equivalence equation. E is equal to mc squared, and in this case it's delta M, it's the mass defect. That's Albert Einstein's equation, to convert from mass defect to binding energy. So the first one will work with the SI units. Okay, so here's the mass in kilograms, here's the speed of light squared, and we get 3.1 times 10 to the minus 11th joules. Nuclear physicists typically don't work with joules, but they do work with MeV. So here's why we had that weird conversion of MeV per c squared. Energy is the mass defect times c squared. If we express energy in terms of MeV per c squared, look what happens when we multiply it by c squared. C squared just goes out. So our answer here is going to be 193.53 MeV. We don't have to multiply. And this is what nuclear physicists deal with, MeV.